Oh, hi Aaron, how are you?
Hi, Dimitri.
Hi Ivan.
Okay.
Hi David.
Hi.
I see. Oh, hi, Fatima.
Hi.
Nice seeing you connected.
Okay, we'll connect the slides by Fatima. Are they projected well? Oh, please confirm if you can see them or if you cannot. I'm using a little bit different setup and trying to share. So you only showing is fine. Good. Okay. Yeah. Many thanks to Fatima for agreeing to present this work. So it is coming to the final stage before submission, and we want to go through final tuning and maybe identifying if there are additional things for improvements. So I am volunteering just to serve as a slide flipper, but Fatima, if you are ready, please go ahead and present.
Okay. So today I'm going to talk about the magnetic field driven dynamics in graphene. Next one.
Okay.
So in the top left panel, we can see the graphene lattice structure. Graphene has a triangular lattice structure with a basis of two atoms. A1, A2 are lattice vectors, and delta 1, delta 2, delta 3, they are nearest neighbor vectors. On the top right panel, we can see the first Brillouin zone. On the bottom left panel, this is the band structure we calculated using the MATLAB code. As you can see, there are 6 K points at the 6 corners of Brillouin zone, and at each K point, valence band and conduction band touch each other, as you can see on the zoomed in image on the bottom right panel. Next
okay.
one.
Would you allow questions as we go?
Sure.
Okay. Yeah. Thank you. it's not critically needed, but it would be great to hear the main goals of the work. And for the technical part of this slide, is it possible? Would you think it would be? So you are writing in your panel C kx in the inverse angstroms. Is it possible to express it in just fraction of the size of the brilliant zone, something that it goes maybe from -1 to 1? I'm not requesting, I'm just checking if some sort of fractional coordinates would be appropriate. And for the panel B, what are the coordinates of the M and K points in comparison to panel C? So can one write down, like, for M point, Kx equals this much, Ky equals this much. For K point, Kx equals this much, Ky equals this much. I believe the reviewer may ask it and or search for this information in the captions.
Okay, so I did not understand what you said about that kx over angstrom, but I did understand what you said about the coordinates in the brilliant zone.
Okay. Okay, I will write you the question about that you about the panel C, and I thank you for acknowledging the question about panel B. So can you tell verbally what are the values of Kx and Ky for M and K point?
It should be 0 and
so Ky is
minus 22. I'm sorry, 22.
Okay. And for
x is 22 and yx is 0. 22.
Yes. 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 And for K point, so Kx is again 22. And what is Ky?
Probably 9.
Okay.
Something like this.
Okay, good. And what is the goal of the whole work? Like, what is the purpose?
So here, if light pulse or any external perturbation is applied to the graphene model, then electron what I understand here in this graphene, that since the valence and band and conduction band touch each other, there is no band gap. So if we apply light pulse, then electron will be excited, and when the magnetic field is applied, then it will influence the motion of electron.
Okay.
And our goal is to study the electron dynamics, photoexcited electron dynamics under applied magnetic field using the time evolution Gaussian wave function.
Okay. And why this dynamics is needed? Is there a challenge for industry, or is there a challenge for theory? Like, why we want other people to believe that it is interesting?
It is important in industry application. Although we are not considering the relativistic direct equation, like relativistic mechanics, but this electron, the probability density of electron moves like cyclotron motion, and if magnetic field applies, then Landau level creates and they can carry information, quantum information. But in our case, we are not considering those relativistic case. We are considering non-relativistic Schrodinger equation.
Okay. So interference can live for a long time. At least there is a hope.
Yes.
Okay, good. Let me know when you want to go to the next slide.
Yeah, next slide, please. So as you know, the graphene has a honeycomb lattice structure. This structure can be described by tight binding Hamiltonian. And if there is no external potential or magnetic field, then one can get the energy band structure from this tight binding Hamiltonian. As we can see the equation, EK equals plus minus something, and here plus for valence band and minus for conduction band.
Okay. And would you please tell what are the definitions of A, B, C, C?
And A, B, there are lattice at the sides.
Okay.
And C, A, C, A transpose, they indicates the annihilates and creates of electron. Epsilon A is the hopping energy, first nearest neighbor hopping energy, and TAD is next nearest neighbor hopping energy.
Okay. Is it possible to, would it be reasonable to flip back to one slide to explain what is A and what is B?
Yes.
Okay. So is it right that each yellow side is A and each brown side is B?
Yes.
Okay. And the lowercase is the probability of jump from one side to another one. Here.
What was that?
T sub AB is hopping.
Mm-hmm. Yes,
Okay.
it's for next nearest neighbor. From yellow to yellow.
Mm-hmm.
And for
Okay.
for yellow to brown.
But here it is AB, so it is from yellow to brown, and I do not see yellow to yellow. Yellow to yellow will be T sub AA.
That is epsilon A.
Huh?
In the first term, there is an epsilon A that is for nearest neighbor.
No, it looks like it is the energy on side energy. It is energy of electrons that sits on side A without hopping. So it's diagonal part of Hamiltonian.
Oh, okay, so then, okay, I see. Mm-hmm. This is on-site energy, yes, epsilon A. And the next nearest neighbor hopping energy, I just ignored that part.
Okay. Okay. And how does one obtain these energies out of the Hamiltonian?
After solving the Schrodinger equation.
So just by diagonalizing this Hamiltonian matrix, right?
Mm-hmm.
Okay. let me know when you are.
Yes,
viewing.
next slide, please.
Okay. I don't know
And
if
this is the part of.
I put it a little, expanded it so maybe it is better visible. So what?
So this is the part of MATLAB code used for calculating band structure in the panel C in the second slide.
Okay. Huh? So plus is for electrons and minus is for holes, right?
Plus is for electrons, plus is for holes.
Please correct me if I'm wrong.
I guess plus is for holes and minus is for electron.
But electrons have positive energy and holes go negative.
Negative. Yes, negative for holes and positive for
Okay, so this one
electron.
is
Yes.
electron and this one is for holes.
Mm-hmm.
Oh, holes. H. So E plus is LUMA and E minus should be then HOMO. Okay, let me know when you want to go to
Yes,
the next.
next slide, please. So since we are considering time evolution of Gaussian wave packet, here first two lines for wave function in position space, and if we calculate first Fourier transform of wave function in position space, we will get wave function in momentum space. That is shown in the three lines. There's a FFT, psi naught x, like these three lines. And the next slide, please.
A brief comment and Yulun, Aaron, and David, please interrupt anytime. I'm just so excited, and I do not have. And I may forget to ask if you have questions, but feel free to interrupt and ask questions as we go. So this slide could be better if you need to present this once again after diagonalizing, after explaining diagonalization of the magnetic field Hamiltonian. Because first one solves the time-independent Schrödinger equation and then time-dependent. So this slide, initial wave packet, relates to time-dependent Schrödinger equation. So it a little too early. Everything seems correct here, but it seems a little too early in the logic to present it, because we do not know, it's misorder. Make sense? Okay. So next slide.
So since we are considering two-dimensional momentum space, so we consider k point along two directions and two indices for two dimensions. And the maximum number of k point, 55. Here we introduced a super index which consists of two indices, I and j, and we calculated wave vector as a matrix. And then the next MATLAB loop, we converted wave function matrix to a vector wave function. Since it is convenient to display wave function as a vector.
Okay. Okay, I see. But right now it does. It is related to initial value of the wave packet for time propagation, right?
Mm-hmm.
Okay. Let me know if you want to go
Yes,
further.
next slide, please.
Okay.
When a magnetic field is applied to a graphene model, then after applying magnetic field, we consider the z direction of angular momentum. And this slide shows how the z direction of angular momentum is derived here.
Okay. So you are telling that for magnetic field orthogonal to the plane of graphene,
Yes.
The only z component of angular momentum participates in the interaction.
Yes.
And one needs only t component of angular momentum. So this part will be used in the Hamiltonian, right?
Mm-hmm.
Okay. And can you tell verbally what will be the next slide before we go there?
Next slide is like how we introduced this z direction of angular momentum and Schrodinger equation using MATLAB code.
Okay, so it will be practical implementation of this operator which acts on different degrees of freedom on x and y, right?
Mm-hmm.
Okay.
So this is the main equation here. As we can see, it is not highlighted, but the arrow, it indicates by arrow. And we can see the equation for z direction of angular momentum as well. Mm-hmm. And another thing is here, we converted 4 indices tensor to 2 indices matrix.
I do have a question. It's a little provocative. I know the answer, but I want to learn from you how you would explain it. So can you please tell why there are these delta functions? So what is the meaning of this unity operator in this line?
When magnetic field is 0, then the electron will be localized at k point, so it integrates by the delta function.
Maybe I'm wrong, but I think it should be different explanation. Can you try once again?
I don't know. Is it the part of Hamiltonian? So one is kinetic energy and the other one is potential. Unity is
No. let's think together. If David, Aaron, or Yulun have an idea what is written here and why this unity operator is needed here. Just any discussion, any suggestion.
It is a diagonal matrix, right? So
Yes, yes.
so it makes the Hamiltonian also diagonal matrix. That's all.
Well, the Hamiltonian in this variable, does have 4 indices. I1, I2, J1, and J2. So instead of square matrix, it is tensor with four indices, right?
Yes.
And then we do know that indices I1 and J1 refer to X dimension, and indices I2, J2 refer to Y dimension. So, and we do know the partial Hamiltonian that acts only on X degrees of freedom. And we know the Hamiltonian that acts only on Y degree of freedom. But overall Hamiltonian should act on both X and Y. So the Hamiltonian is composed of product of these two objects which have non-coinciding indices. So when we perform activity in respect to X degrees of freedom, the Y degrees of freedom are staying unchanged. When we perform activity in respect to Y degree of freedom, the X degrees of freedom stay unchanged. So this is needed to implement operators for 2 degrees of freedom. And if maybe there will be a problem project that Yulun will do in the future for either making chemical reactions with 2 reaction coordinates, or 1 reaction coordinate can be nuclear degree of freedom and another can be photon. Then we will need to implement the same idea. So when one operator, when we want to build the overall Hamiltonian, when it will be composed of parts. So one partial thing affects only degree of freedom 1, and then it needs to multiply it by this unity operator in respect to second degree of freedom, and then opposite. When we affect second degree of freedom, the first one should be represented by unity operator, because overall number of dimensions should be kept. Like if there are 2 independent variables, the operator should have 4 indices. Make sense?
Mm-hmm.
Okay, and you did put another arrow for the angular momentum. Would you please give comment about this implementation of angular momentum?
So as we can see in the equation, it's the first, on the right hand side, first term is, looks like first term is px. It should be the other way around.
Okay.
So in the equation, it shows that first Px, then x
Okay, so
minus xpy.
it should be d
First term is pxy minus x py.
x times y, right? Then second part should be x times y, right?
Yes.
And since x and y degrees of freedom are counted by different independent variables, the arguments for this px and y are non-coinciding. So it's I1 J1 and I2 J2 for x and y components. Okay. And I do believe that in addition, this operator, angular, is given angular momentum in Cartesian coordinates, right? In space.
Mm-hmm. Yes.
And if you present the few lines of code below, there should be similar operator for angular momentum in momentum space. So it's something like angular p, right? Okay. Please let me know when you want to.
Next slide, please.
Okay.
And in this slide, it shows how we coded time evolution operator in MATLAB.
Very good. So there are three lines that look very similar to each other. Do you remember which one of them is used later? Which one is correct? So with imaginary unit, with minus or with plus?
I think middle one is good.
So
Middle equation.
Maybe I would check maybe the first one, but we can double check later. And this segment in here should be the full Hamiltonian for the system in magnetic field. Should be like H equals H naught, which is tight binding minus magnetic field times LZ. And then this Hamiltonian is plugged into the evolution operator.
Mm-hmm.
Okay.
And the next slide, please.
Mm-hmm.
This slide shows how we inserted time evolution operator into the wave function.
Mm-hmm. Okay. So I do have a question. Should be there Bohr magneton in front of this interaction term, or we in the units that we selected can be skipped?
It was selected as 1.
Okay, But if we would write equations in general, one may put this proportionality constant. Okay. So what's the name for this procedure?
Which procedure?
Solution of independent Schrödinger equation by evolution operator. Would it be correct? Or there is a better name for this?
I'm not sure.
Okay. So you do not mind call it evolution operator for time-dependent Schrödinger equation?
Oh,
Okay.
never do that.
So up to okay. I think there is one slide missing. Let me
Yes,
edit.
that-
Let's edit together right now. Just make it as so tight binding Hamiltonian minus LZ magnetic field, and then one is applying this full Hamiltonian to the unknown wave function, and this will be an equation to find for wave function in the momentum space. Right? So time independent Schrödinger equation. And all slides up to here were methods, and in the next slides you are going to present results, right? Okay, let me know when you want to go to.
Yes, please. Here we can see the eigenstates. We calculated 500 eigenstates. Here we can see for each value of magnetic field only 3 representative eigenstates and their corresponding energies. And these eigenstates are shown in first Brillouin zone of reciprocal space.
Okay.
For a lower value of magnetic field, looks like the electron probability density distribution is localized around the K point, and if the magnetic field is higher, then the electron probability distribution delocalizes around the K points.
Okay. Other questions from David, Aaron, and Yulun? Any suspicion? Any just something seems missing?
So how do the
yes, please.
So how do these figures relate to the dispersion cones that are shown in as example for figure 1? Like how do these states relate to those? Because so I would think if you could find the state.
Actually here, here in this electron probability density distribution, we consider only in conduction band. So we did not consider valence band. So it's just the conduction band. So and each corner is one cone in the Brillouin zone.
Aaron, are you satisfied or you want more? Let me bring the dispersion curve and copy paste it into here so we can look at them together for better analysis. But it is the very relevant and great question.
I think I realize now my question doesn't make sense because the dispersion, I think the dispersion curve is just energy, right? It doesn't relate to probability densities in the Brillouin zone.
So what I understand your question is how this electron probability density related to the cone in the Brillouin zone, right?
Right.
For these electron states, we consider only the conduction band. Right? If you look at this band structure, we consider only the conduction band.
So then in the conduction band, like where would you, if you just considered the lowest point of the cone, like how would those states be distributed?
Yes.
In momentum space?
So if the state number is 1, that would be the lowest one. But here the state number is, if you look at the top row, the first one is state 171. So it should be somewhere like higher than, so it's not exactly at the lowest point of the cone, it would be higher than the lowest point. You know what I mean? Since we consider like, so if the conduction band is divided by many states, right? So we consider 171, 251, and 351.
All right, so I guess my question would be, as a reference, like what would be the distribution without the magnetic field? Like, does it change the distribution very much?
You mean, does the distribution depend on the magnetic field?
Right, so I guess.
Yeah, it depends. Like the electron distribution depends on the magnetic field. If the magnetic field is higher, then the electron probability distribution will be delocalizes.
Mm-hmm. So in the limit of no perturbation, I guess your states would be more localized.
Without perturbation, yeah, more localized. If there is, the higher the perturbation, the electron probability distribution will be delocalized, more delocalized.
Without magnetic field, the momentum is conserved, and eigenstates will look like two-dimensional delta functions. So on this colorful diagram that Fatima is showing, the eigenstate without magnetic field will be only one dot, 1 point. And as magnetic field increases, the eigenstate is distributed over several dots. And I hope to hear from Fatima the following keywords at the end, at the time of conclusions: that magnetic field violates conservation of momentum. Because without magnetic field, the momentum is conserved. If we set up electron in the plane wave state with certain momentum, it will be certain for eternity, forever. But if there is a magnetic field, then momentum is changing. So it's one aspect. Another aspect of the question by Aaron, which is very, very, very relevant. This potential curve, the conduction band that we are focusing at, can be approximately considered as potential energy surface. It is not potential energy surface, it is dispersion. It depends on momentum, it is more kinetic energy rather than potential. But in some sense, it is energy profile, and we can find eigenstates in this analog of potentials. So it will be some peaks which will be maxima above the minimum of the potential, right? And if there is external perturbation, the shape of this eigenstates will be perturbed. But there is a challenge for human brains. As soon as we apply magnetic field, we cannot plot the Hamiltonian in the as this potential dispersion curve, because the Hamiltonian is four-dimensional, and this line would become discontinuous. It will be something that humans' brain cannot imagine. So it's more reasonable to speak only about eigenstates, which we still can imagine because they're two-dimensional. Another thing, before we switch on magnetic field, there is a one-to-one correlation between value of momentum and value of overall energy. So we can draw this shape. As soon as we launch magnetic field, momentum stops being a good quantum number, and energy cannot be drawn, can be defined as function of momentum. We can only list eigenstates, and eigenstates themselves will be distributions as function of different values of momentum. So I understand the concern that you try to express. The things that Fatima is presenting and we are considering is away from ability of human to imagine everything in a mechanical way. So we can compute it with equations and codes, but by human brain we cannot imagine the objects that we are describing. Does it address your question in part?
Mm-hmm. Yeah, I have a little bit better idea of how to look at these figures.
Okay. And I foresee that reviewer of this of the paper, when it is submitted, will ask questions like this. Even if all results are absolutely correct and interesting and relevant, there is a challenge for human to understand it, and it will be discussion between reviewers and authors for sure on this aspect. So question of Aaron is very relevant, and it at least prepares authors to address questions of reviewers in the future.
Okay, next slide.
Okay.
On the top panel, we can see the density of states at different magnetic field values. First, density of states for without magnetic field. We can see if the magnetic value of magnetic field is increasing, the density of states are decreasing. The blue line and yellow line represent conduction band and valence band respectively. On the bottom panel, we can see the first 50 eigenstates and their corresponding energies. Although we have calculated 500 eigenstates and their corresponding energies, as we can see, when magnetic field, the value of magnetic field is increasing, and the energy of lowest eigenstate is decreasing, and it will be continued for higher magnetic field.
Okay. Fatima, would you think it is possible and relevant to show the density of states in a narrower range? Because this going of the density of states down after energy more than 0.5 is when we go away from Dirac-Cohen region, and it will need more discussion. It could be an artifact of calculations, or even if it is a true thing, it may need explanation. So I think it will be easier to present if you focus only on the energy range close to Dirac-Cohen, in vicinity of 0. So it would be really great. There is another thing that I do not know how to interpret, and like two things, and reviewer may come after us. So first thing, there are 6 Dirac cones in the Brillouin zone, and in the 0 magnetic field, energies of these 6 cones should be equivalent, degenerate. So one would expect to have 6 degenerate points at lowest energy, but by some reason we have 4 rather than 6. I will be reviewer rather than co-author. I would complain and ask why this is happening. So, if anyone has an idea, please express. So we need to figure it out and address before submission. Like here is magnetic field, it looks like almost degenerate, and then the next batch looks closer. So this one it looks better. For description of this graphene, when Fatima is presenting the model, it uses this A and B vectors, which are, or A1 and A2, I think A1 and A2, which are not orthogonal. A1 is not orthogonal to A2. And maybe in order to model the things, instead of X and Y, one needs to use different set of coordinates, like A1 and A2 as coordinates which are not orthogonal, and then it will be more reasonable. Or maybe one needs to redo everything in polar coordinates, like distance from gamma point and then the angle. It doesn't seem possible to do it in a short time, but at least some ideas to understand and address this inconsistency would be great.
So you mean that I need to do this before submission?
Only verbal explanation. I do not believe that we can redo the code. If we try to redo the codes, it will take at least 2-3 months to debug and make it working. But we can verbally address that we do see weaknesses, and we know where they originate from, and we know how to fix them in the future.
So it can go out to discussion then.
Yes, exactly. So another thing, in panel D and E, the energy of the orbital in the conduction band is bigger than 0. And in panel F, there are several energies with energy which we attribute to conduction band is smaller than 0. So this is also, I wouldn't say wrong and suspicious, but it is something very novel and mind-throwing. So we need to be ready to explain to reviewer how to interpret it. Of course, we can remove this result and not show it, but a smart reviewer will ask about it. So it's better if we develop an explanation. So having few states from conduction band dropping down the 0, the Fermi energy, would probably correspond to several states from valence band to penetrating into conduction. So it is mutual penetration of valence and conduction band. And it seems like conductivity, magnetic effect for conductivity. So if this is true, this would mean that increase of magnetic field would increase the conductivity. So let's plan on thinking and discussing this in at least between us and at most in the discussion section. So it seems like mutual penetration of conduction band and valence band. So this negative values of energy. May I ask if there are questions or comments on these aspects from David, Yulun, or Aaron? Do you see major problems or major suspicion, or it seems like a technical issue that is okay to explain verbally and as a natural effect rather than artifact of computation? So I would probably check keywords in literature for magnetoresistance and magnetoconductance. So if increase of magnetic field can change the conductivity. And this is not the main aspect of the paper, but it if everything is correct here, it can be a big breakthrough and will attract citations, so it will be something substantially novel. And so we shouldn't fear, but just try to interpret. Whew, okay, let me know if when you are ready for the...
Next
okay.
please.
Should I run the video?
Yeah, and this is the movie of 500 eigenstates at 0.7 Tesla. It is very slow.
I think when we do video, when we transfer video between computers, it may skip some snapshots, so it should be continuous snapshots. Can you explain what to see and how to interpret it?
So electron distributions are changing with the corresponding number of eigenstates, right?
So since 500 eigenstates is too large, it is quite a challenge to show all of them as panels in figures. And instead, Fatima is showing scanning through all eigenstates as a movie. And one can see that some of them are localized near the red dots, and some of them form shapes in this momentum space.
It's kind of confusing because with increase of time, you are also changing the eigenstates.
Sorry, I apologize. There is no time here.
Okay, so this is just a final distribution of eigenstates, right?
It's just a scan. So we do have, let me do a little drawing. So we do have phi sub I of kx, ky. And to avoid the imaginary part, we do square. And then we run for the index from 1 to 500 and just show them. But there is no time. They all are static.
Okay.
Okay. Fatima, do you have more comments, or you want to go to the next one?
The next one.
Okay.
And this is the same thing, eigenstate, 500 eigenstates at magnetic field 1.93 Tesla. Here we can see that electron distribution area is more localized, delocalized.
Delocalized. Okay. Can you make a comment about this delocalization of the eigenstates and the cyclotron trajectories?
I'm not sure. So in the next slide.
No. Before we go to the next, if the can you tell what are cyclotron trajectories? And we here are chemists. You have a physics background, so just teach us what are cyclotron trajectories.
So if magnetic field is applied to a free electron, then electron moves in a circular motion according to the Lorentz law. So.
Okay. So, which means that eigenstate, if you convert this classical trajectory into the eigenstate, then it will be like a ring in this axis. So in kx, ky, if it corresponds to cyclotron motion, it will be some probability on the surface of a circle and 0 inside and outside, right?
Mm-hmm.
So it is how we should interpret this eigenstates, and some of them show this circle-like shapes. Maybe not exactly, but something circular. And it is very expected and very positive results. So this should prove that we do something in the right way, and this should satisfy the reviewer. So it's a good point. Okay. And Any
Next.
other? Can you, before we go to the next slide, can you please tell what should we expect in the next slide?
The next slide is electron probability density distribution under applied magnetic field.
I can pretend that I do not understand you. On this slide that we are watching right now, it is also electron density distribution under applied magnetic field. What will be new?
This is static, and the next slide will be dynamics. So.
Okay, so before, until now, we were solving time-independent Schrödinger equation. And starting from the next slide, we will look for solution of time-dependent Schrödinger equation, right? Okay.
Here we can see the snapshots at different instant of times. Snapshots of electron dynamics of electron probability at density. As we can see, if we apply higher value of magnetic field, this electron probability density distribution is more delocalized.
Mm-hmm.
And we
Yes.
are just for simplicity, we consider only one direct point, but it's supposed to be happen from all of these 6 direct points. If we consider the motion from all of these all 6 K points, then they should form a cyclotron-like trajectory.
Okay. Is it possible to say that when we have smaller field and longer time, the shape is approximately the same as if we have larger field and shorter time? Is there similarity between these different time points in different time steps?
Yes. Mm-hmm.
So approximately increase of field or looking for a longer trajectory will give the same results. So with larger field, it just moves quicker. Okay. I do have another question. Based on the discussion in the previous slide, I would expect that this initial distribution will just move on a circular trajectory here and there, but instead it splits on several pieces and it forms interference fringes. Can you please share your vision why it creates these interference fringes?
I'm not sure.
Just try if it's inside the group, so if it is not quite adequate.
As I understand, then if electron, if it's like a kind of interference, constructive interference.
Yes. But why electron cannot go completely on a circular orbit? Why it splits on several peaks?
I'm not sure.
And everyone is invited to contribute ideas.
My first thought would be spin, but it doesn't seem like you account for spin variables for your density. Is that correct?
There is no spin here.
there is no spin. So let's just utilize this analogy with eigenstates in the potential. So if we start from Gaussian wave packet above the minimum and then assign it to move in a certain direction, in the free space it will go wherever we send it. But here, when it is inside this minimum, it hits the wall of the Dirac cone and reflects back. So we do create bound states. So it's eigenstates in the vicinity of the Dirac cone, and bound states like S, P, D in hydrogen atom, or in the square box, it is n equals 1 and n equals 2 states with different number of fringes. So it looks like signatures of formation of eigenstates in the vicinity of the Dirac cone. So one may try to interpret formation of these fringes in terms of eigenstates that we discussed on previous slides. So if the value of magnetic field is not sufficient to jump over the potential barrier, so here there is a barrier, and if the magnetic field is not strong enough, then instead of overcoming the barrier, it will bounce forth and back, and it can be decomposed. It can be expressed as a superposition of eigenstates which are localized in vicinity of this Dirac cone. I can be wrong, it's only a hypothesis, but I invite you to criticize or discuss if it sounds possible explanation.
If this is the case, can you just track some of the eigenstates instead of the wave packet? Like the high energy one?
What do you mean track? Just look at them, or start dynamics from eigenstate?
I guess you can do it both ways.
Huh?
I guess either of them works. So I guess my point is, for eigenstates with high energy, you can just overcome the barrier, right?
Yes. So we can either I'm not telling that we need to do any calculations right now. It's more time for analysis. But if we hypothetically do more calculations of the dynamics with higher value of magnetic field, then wave packet will penetrate into different Dirac cones. It will overcome this barrier on one hand. Or on another hand, if we start from the eigenstate with large energy rather than Gaussian wave packet, it will be automatically spread over the whole brilliant zone, and it will be long-lived circular-like state. So if there are no more critical suggestions, let's Fatima, when you are ready, let us know if you want to go to different
Yes,
slide.
next slide. So this is the movie of dynamics of electron probability distribution at a 0.7 Tesla.
Huh? It doesn't. Oh, this one doesn't play. Okay, I do not want us to lose the opportunity to watch it, so I'll bring it from YouTube. I think we should have it on YouTube. The second, I will be very quick. So first we want the So I believe this movie created by Fatima scans over very short time for like 25 femtoseconds. And the step is a small fraction of femtoseconds. So as movie goes, we go quite slow. And what we see here, instead of Gaussian wave packet moving as a whole entity on a circular trajectory, it splits on pieces and forms these fringes.
The PowerPoint slide is still showing.
Oh, okay. Okay. I'm watching and enjoying it, but okay. Let me. Okay, sorry. Let me do it. So there is nothing, and I will. You see the YouTube browser and YouTube video right now? Please say yes. I do not see it right now. Okay. So now we are coming closer to the end of the trajectory, and I did set up a loop for. So by now it's about the end of trajectory, and it has several fringes, and it will start from the beginning. So Gaussian wave packet. It changes shape, and also it looks like first it squeezes instead of becoming more broad, which is also a little interesting. And then after some time it starts becoming broader and splitting on several fringes, on several peaks. Fatima, do you have any comments about this movie?
No.
Okay, let's watch another. So this was the lower value of magnetic field.
I think this one is for higher one.
No, it tells 0.7 Tesla. Maybe I misinterpreted and uploaded different one. And here is the one for bigger value. So if I'm wrong, it will show less dynamics, and so in my labels it is 1.93 Tesla. And now we are about third of a trajectory, and it looks like a half of the trajectory with.
So I think you uploaded the same one.
Okay, and this seems, you think I did upload it the same one under different names?
Yes.
Okay. You may try to upload the right ones and share the links, but after the meeting.
But I don't know how to do this way.
Oh, okay. Okay, so I did. Are we still on the connection?
Yes.
Yes, I think we. Okay. Okay. Yeah. So, do you see the Fatima? Is it? Am I showing the right slide right now?
Yes.
Okay. So
here we can see the trajectory of expectation values of momentum at two different magnetic field. And we can see I indicated arrow, indicated the direction of the trajectory with arrowheads.
Okay.
So it starts, both of them starts from the coordinate 22.08 x coordinate, and y coordinate is 0.
Okay, so the black point in panel A and and panel B are the same. And why the first, what is shown? Can you please explain what is this expectation value of Px and Py?
How it calculated, or
No, what it is, how to relate it to the movies, to the dynamics that we were discussing on the previous slide.
At the center of that bright fringe is moving in this trajectory.
Okay, so it's center of the wave packet.
Center
Okay.
of the wave packet.
And it starts in the same point because we have the same initial condition. Now, it looks like overall motion of the center is very small. It changes by like less than 0.1 in this px units. But why does the center move in the opposite directions?
I'm not sure.
Or can one
Looks like for
interpret it?
higher value of magnetic field, it moves the opposite direction.
Or one should interpret that it starts moving the same direction initially, and then they have different curvature. But still, we may want to interpret it. So this different curvature as function of magnetic field does not match classical electron motion. It should deal with fringes and quantum features of this eigenstates inside the core. Are there any questions or comments? Okay, if there are no, Fatima, please let me know when it will be time to go to the next slide.
You can go to the next slide now. Here for magnetic field 0.7 Tesla, we can see the trajectories of expectation value of momentum from two different initial positions. So for 0.7 Tesla, this trajectory is always in the same direction.
It is good.
And I was not able to calculate more trajectories for the 1.93 Tesla.
Are there objective difficulties, or it was just not enough time because we discussed
Not
it?
enough time. It takes time.
Oh, okay. I do have a question, not as a co-author, but as a reader, just for curiosity. If one would continue the dynamics for trajectory started at gamma point, would it show a spiral with including radius? For magnetic field accelerating wave packet moving on a circular trajectory with a bigger diameter, or it will just go and settle into one of the Dirac points and then we'll stop there.
You mean if the magnetic field is higher?
No. Same value of magnetic field, but longer trajectory. So instead of 25 femtoseconds, look for, I don't know, 4 times longer, like 100 femtoseconds. And it doesn't mean to do calculations immediately. We can just hypothesize.
I think it will go one of the Dirac points.
Okay. Okay, very good. Is there any? Okay, and in the next slide, I did copy-pasted conclusions from your draft of the paper, which we may go over briefly
I can conclude by
Verbally.
talking about a
Okay.
couple of points.
Please.
So graphene, we can see from the band structure, graphene shows non-trivial dispersion in the band structure, and the energy dispersion is linear around the direct points. That is useful for electron dynamics by driven by photo excitation. That's what it's written here. And then the applied magnetic field leads to violate a momentum conservation. And the dynamics of electron probability distribution tends to form cyclotron-like trajectories.
Okay.
These are some of conclusions.
Okay. Anything else you want to highlight?
There are more points here, I can see.
Okay. If you want, you may highlight something that you believe is important.
This
Or those.
study can be helpful in graphene-based optoelectronic devices.
Okay. Okay. Yeah. Excellent. So please join me in thanking Fatima for very interesting and brave presentation, because it goes very much beyond standard things that we are doing. So it was vivid discussion during the presentation, but maybe if anyone has more questions, please feel free to continue the discussion and ask more questions.
Kind of more of a general question, but is graphene diamagnetic or paramagnetic?
I don't know. Fatima, do you know?
I don't know.
So is it increases magnetic field in internal induced magnetic permittivity? Is it increased when you place a magnetic field, or it resists? Yeah, let's check it. Let's check it. And Aaron, why do you ask?
Oh, it's just, I don't know, it's been beaten into me whenever I see a circulating charge. It's going to produce its own magnetic field. So then my thought was that's additive or tries to expel the external magnetic field.
Are the metals diamagnetic or paramagnetic? Metals like with paired electrons. If the metal doesn't have unpaired electrons, I'm not considering like iron or manganese. Are metals diamagnetic or paramagnetic?
I guess I don't know. Yeah, I don't know off the top of my head.
Okay, we may check on this, but it should have some similarities to metals, because it is zero gap, and it's like zero gap semiconductor, but it has some common features with metals, and it may be in response to external magnetic field. In the macroscopic features, it should be similar.
Mm-hmm.
Okay. Any more questions or suggestions? Yulun, do you see that this code will seems easy to be ported into chemical applications for motion in 2 dimensions between 2 reaction coordinates, or you see some challenges in practical implementations?
I'm not so sure.
Because it could be a natural continuation of these activities, and maybe in the fall semester when there will be undergraduate students in the PChem lab, some of them will be willing to try, and then we can continue after them by converting this code from physics domain to chemistry domain, because some reactions have explicitly like 2 or even more reaction coordinates, and it seems reasonable to try. Okay. I believe next time it will be Meet Erickson, who presented, who took computational chemistry a year ago, and now he is trying to run the codes created by Yulun for fragmentation of polymer. So I think it will be fun, although he's not doing too many calculations, so he may have questions to us, because he's at the initial part of his life as computational chemist. Okay. Let me thank Fatima and everyone for the discussion. So many thanks. Meeting is complete. Meeting is done, and let's just meet in a week from now. And if there are any questions, let's exchange emails and make one-to-one Skype meetings if needed. Okay, so I suggest we finish the meeting and disconnect. And I believe recording was going well, and I hope it was going well, and I plan to share it when ready. Okay. Oh, but wait, quick question. Do you see any worse or better quality of the image and transmission? Because instead of browser, I was using special app for this connection. Is it absolutely the same, worse or better?
It seemed to be a little smoother.
Okay.
I think it cut out for a little bit. I think that might have been due to like your computer just being overwhelmed.
Okay. Yeah. Thank you. Well, if there are no requests for quick questions, let's disconnect now.
I have a question. Like Amir asked me to tell you that he's waiting for your response.
Oh yes, please tell me that I read. He asks some complicated questions. I want to answer all of them at once, and it is not easy. Probably we need to set up a Skype meeting with him. But I noticed his email, and he's doing right things. So tell him that I noticed his questions.
Okay.
Yeah. Thank you. Bye-bye.
Okay, see you next week.
Yeah, see you next week.
Bye.
Bye.